Hi, in this video I'm going to talk about the convergence of Fourier series to the function itself. And first of all, we should understand that if the Fourier series converges, it doesn't imply that the Fourier series indeed converges to f. For example, for the identity transformation fx equal to x for x inside interval negative pi to pi, we know that the second derivative of f is equal to 0. So indeed, f double prime is an integrable function. But according to our theorem in the last video, we know that the Fourier series of f converges. But remember, we have studied this example and we know that the Fourier series do not converge to f. From this example, we see that although the Fourier series of f converges, the Fourier series of f does not converge to f. So, how can we study the convergence of Fourier series to the function itself? Well, first of all, we should express the partial sum of the Fourier series in a closed form first. And therefore, we first introduce the identity here, which is the sum from k equal to 1 to n. Cosine k theta is equal to sine n plus 1/2 theta minus sine 1/2 theta over 2 times sine 1/2 theta for theta, which is inside interval negative pi to pi except 0. And how can we prove so? Well, I use a trick. I first multiply the sine 1/2 theta to the left hand side, and we get this expression. Well, then we use the product to sum formula to obtain the second line. The second line is sine k plus 1/2 theta plus sine 1/2 minus k theta, and then we multiply by 1/2. And we rewrite this expression as negative sine of k minus 1 plus 1/2 theta. And indeed, this is a telescoping sum, and therefore we are left with the first term and the last term, and hence it is equal to sine n plus 1/2 theta minus sine 1/2 theta times 1/2. Theta is non-zero, then sine 1/2 theta is non-zero, and therefore we can divide the sine 1/2 theta to the right hand side to get our identity. Then what will happen if theta is 0? Well, we see that cosine 0 is equal to 1, and therefore the sum of cosine k 0 from k equal to 1 to n is indeed adding 1 n times, and therefore this sum becomes n. And after proving this identity, we are ready to express the partial sum of the Fourier series in closed form. And we let the partial sum to be SNFX. So, by the definition of SNFX, it is equal to A0 plus the sum from k equal to 1 to n, AK cosine kx plus BK sine kx. Remember what A0, AK, BK are. A0 is equal to 1 over 2 pi times the integral from negative pi to pi of f, and AK is equal to 1 over pi times the integral from negative pi to pi of fy cosine ky, and BK is equal to 1 over pi times the integral from negative pi to pi of fy sine ky, and therefore the first line becomes the second line. And notice that it is the compound angle formula form, and therefore this expression becomes cosine k times y minus x. And by the linearity of the integration, we know that the third line here will become the fourth line. Next is to apply a change of variable z equal to y minus x, and therefore y is equal to x plus z. And therefore the previous expression becomes 1 over pi times the integral from negative pi minus x to pi minus x of 1/2 plus the sum from k equal to 1 up to n of cosine kz fx plus z. And recall the previous identity. The previous identity said that if z is non-zero, then the sum from k equal to 1 to n of cosine kz is equal to this expression. And if z is equal to 0, then the cosine kz here will become 1, and this is equivalent to adding 1 n times, and therefore it is equal to n if z equals to 0. And therefore we can write the star here to be the integral from negative pi minus x to pi minus x of dnz fx plus z dz, where dnz is equal to sine n plus 1/2 z over 2 times sine 1/2 z times pi if z is non-zero, and it is equal to 2n plus 1 over 2 pi if z is equal to 0.